Welcome back. In the previous video, we filled an STM-1 frame with ATM cells and got 83.17% user data efficiency. Today, same frame, different filling. We replaced the 53-byte ATM cells with 576-byte IP packets. Each IP packet has 24 bytes of header, the IP header plus protocol stack overhead, and 552 bytes of actual user data inside. 4 questions, same shape as last time. Part A. How many complete IP packets fit inside the payload area of one STM-1 frame? Part B. How many bits of actual user data does that give us per frame? Part C. What percentage of the total STM-1 capacity is genuine user data? Part D. At what rate is the user information being delivered in megabits per second? And of course, we will compare against the ATM result. Will big packets do better? Will the unused tail bite us? Let us walk it. First, a quick recap of the STM-1 frame. 9 rows by 270 columns of bytes. That is 2,430 bytes per frame. And at 8 bits per byte, exactly 19,440 bits per frame. The first 9 columns are section overhead, 81 bytes per frame total. 3 more columns are path overhead, 27 bytes per frame. What remains, 258 columns by 9 rows, is 2,322 bytes. This is the payload area we get to fill. And the frame still runs at 8,000 frames per second, 125 microseconds each. These numbers do not change between videos, only the way we slice up the payload changes. Now the IP packet, 576 bytes total. Historically, the minimum reassembly size from RFC 791, the default safe packet size for IP over wide area links. Of those 576 bytes, 24 bytes are protocol header, 20 bytes of standard IP header, plus a small allowance for options or upper layer encapsulation, and 552 bytes carry actual user data. Per packet, 576 bytes shipped, 552 of them are real information. Packet level efficiency, 552 divided by 576, about 95.83%. Compare that to the ATM cell, 88.7%. The IP packet is more efficient at the packet level because the header is fixed at 24 bytes regardless of how big the payload is. The bigger the packet, the smaller the header looks proportionally. Already, before we even count tail waste, we are saving 7 points of efficiency. Part A. Packets per frame. Payload area, 2,322 bytes. Each packet, 576 bytes. 2,322 divided by 576 equals 4.031. Round down to 4. Packets are atomic. You cannot send half a packet. 4 complete IP packets per STM-1 frame. Total bytes occupied by those 4 packets. 4 times 576 equals 2,304 bytes. 18 bytes of payload sit unused. Notice, just 4 atomic units fill the frame, compared to 43 ATM cells. Bigger pieces means fewer pieces means less tail waste. Only 18 wasted bytes versus 43 for ATM. Part B. User data bits per frame. Each packet carries 552 bytes of user data. 552 times 8 equals 4,416 user bits per packet. 4 packets per frame times 4,416. That is 17,664 bits of actual user information per frame. Part C. Efficiency. 17,664 user bits divided by 19,440 total bits equals 0.9087 or 90.87%. Compare that to ATM's 83.17%, an improvement of 7.7 percentage points. Where did the savings come from? Two places. 1. The IP header is 24 bytes per 576 byte packet, about 4.17%. ATM was 6 bytes per 53 byte cell, about 11.3%. Bigger packets simply spread the header over more user bytes. 2. Only 18 bytes of payload tail wasted instead of 43 for ATM. Part D. Data rate. Each frame carries 17,664 user bits in 125 microseconds. 17,664 divided by 125 microseconds equals 141.312 megabits per second. Compared to ATM's 129.344, IP delivers about 12 more megabits per second of useful data through the same 155 megabit per second pipe. Same line rate, same overhead, but the user gets more. 3 takeaways from this exercise. 1. Bigger packets are more efficient at the cost of latency predictability. IP packets up to 1500 bytes can flow through this same frame, pushing efficiency even higher. But a single big packet hugging the line means a voice call has to wait its turn. ATM chose small fixed cells specifically to keep voice latency low. IP chose variable larger packets specifically because data flows benefit from amortizing the header. 2. The unused payload tail tells you how good the size match is. 43 bytes wasted with ATM, 18 bytes wasted with 576 byte IP. If you happen to pick a packet size that exactly divides 2322, the tail goes to 0. 414 byte packets, for example, but no real network uses arbitrary numbers like that. 3. In the next video, we will mix two packet sizes in the same frame, 53 byte ATM cells alongside 77 byte cells. We will see how the answer changes when the payload is heterogeneous and which configuration squeezes the most user data out of the same 19,440 bits. Same frame, different fillings. The answers keep getting more interesting.